It's time to start class. How many of y'all are ready to? Is everybody signed in? 1, 2, 3, 4. 1, 2, 3. Nope. Here you go. How many of you are ready to see if we can make some heads or tails out of the observations we had yesterday in lab? How many of you were here for lab yesterday? Yeah. Well, we're going to start chapter 21 today. We did finish up with the, we did the Ampere's law and the magnetic field in the solenoid and then the toroidal solenoid. All right. And does anybody have any homework to turn in or any questions from your homework? $49? You weren't here last time, were you? Were you here Monday? Number 49 was one we did. We did it in class. No, we'll do it again. It's not that long. It's just Ampere's law. There you go. Got toroid. A solenoid in the shape of a toroid. So you got I coming in here, I going out here. Now, it says use Ampere's law to calculate the magnetic field at this radius inside the toroid, inside the solenoid, and at this radius outside the toroid. Little r and big R. Well, Ampere's law says if you add up all of the parallel components of the magnetic field, all the little bits of the magnetic field parallel to your line of summation, your path of integration. Okay, y'all have all taken it, right? Okay, so I'm going to say path of integration. You're integrating around that circle. Okay, and you add up all the little parallel components of the magnetic field at every little delta L length. Okay, sum them up over a closed loop. And that will be equal to mu sub naught times the current enclosed. Am I forgetting a factor there? Somebody look at your... Is that the complete formula? It's mu sub naught times... You got it on your notes? Yeah, mu sub naught I enclosed. That's the total current enclosed. Okay, well, when you do that summation all the way around, you get what's your total length? It's the circumference of the circle, which is 2 pi times the radius times b sub naught. And that is then equal to mu sub naught times the current enclosed. Well, every time you pass one of those little coils, you get that current adding into it. So that I enclosed becomes the number of turns times the current. As long as you're inside the solenoid. As long as R is greater than this and less than that. Okay? Well, that gives you B is equal to mu sub naught Ni over 2 pi R. And what's mu sub naught? Like 4 pi times 10 to, doesn't matter. That's the magnetic field inside the solenoid. Now, if you go to the outside radius, and I would point out to you that this would also be true if you go to an inside radius, either one of these R's. Now, what is your net current? You have I coming in. You also have I going out. So in this case, your magnetic field goes to 0 because I is, your net current enclosed is 0. The same would be true if you went in a smaller radius, anywhere inside that toroid. Your total current enclosed is 0, your magnetic field is 0. What this is telling you is that when you bring the two ends of that solenoid together, you contain all of the magnetic flux to the inside. It's the fringing effects that we saw on a straight solenoid, where the magnetic field fringes out on the outside. It becomes like a big bar magnet. That goes away when you close the two ends together. Now, here's the important part. So make sure you get this in your homework. Is the magnetic field inside this toroid constant? How is it not constant? No, 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 nothing as complex as all that. That radius is not constant. R is lower here, and is smaller here and bigger here, which means B, the magnetic field, is denser here and more rarefied there. It varies the magnetic field varies inversely with radius. So it is not uniform and constant throughout the whole inside of the solenoid. If it were a straight solenoid, it would be. It would not matter at what radius, at what distance inside you did your summation, you would get the same result. But you would also have the fringing field outside. You bring the two ends together, the fringing field goes away, but now the magnetic field inside varies inversely with R. And if you think about it, it kind of makes sense because look at all of those coils. As you go around the loop, they're going to have to necessarily spread out a little bit on the outside. You spread them out, your field gets a little weaker. All right. Any more questions? How many of you have labs that you've got to make up? Homework assignments you've yet to turn in? Okay. The deadline, so to speak, is the end of next week. Go on spring break after next week, which means I have to get busy getting all of the work that y'all didn't do all summer, all semester long, getting it graded in 1 week. But, yeah, thanks. I really appreciate that. I don't think I would get to keep my job very long if I let that happen. And I really like this job. You need to get your labs done. You need to get any homework assignments that haven't been turned in. Like I explained before, I'm not going to refuse to accept them after next Friday, but I'm also not going to promise they'll get graded after next Friday. Because after next Friday, you turn in something late, I will grade it if I get a chance, if I can. But the later it is, the older stuff will wait the longest. So after next week, your homework needs to be turned in on the Monday of the following week. This week's homework would need to be turned in on the next Monday. If it's turned in on next Wednesday or next Tuesday, it's late. It'll go to the top of the pile of late work to be graded, but it will go to the late work pile to be graded, which means it may or may not get graded, depending on how busy I get with everything else. And if you have something from week 1 that you turn in, well, you're going to have to hope I have a really smooth, a really smooth end of the semester to get to grade, to get that graded. Okay, so, just giving the heads up, I really do want y'all to get this done because I do not want. I mean, I want you to earn points. I want you to learn the material. So, let's go ahead and move on to chapter 21, electromagnetic induction and Faraday's law. Who can tell me what induced EMF is? Or just any kind of EMF? EMF. Electromagnetic force, or electromotive force is what it actually stands for. It's why it's a force. It pushes electrons. And what are the units of EMF? Volts, thank you. Not a trick question. The units of EMF are volts. That's what you measure. You measure volts. This is also why, I don't know, maybe they've changed it, but when I was learning it, Ohm's law was written I equals E over R. Not E field, but electromotive force. In fact, that's why they use the script E for electromotive force now, instead of the uppercase block E, because that one looks like E field, which is a vector field, not the potential field, the voltage. So, everybody already knew that if you had a moving electric charge, a moving current in a wire, it would produce a magnetic field. And they knew that if you had a magnetic field, it would exert a force on an electric current, on a moving charge. Then along came Michael Faraday and some American named Henry, I think, who both kind of at the same time discovered, they asked the question, if a moving electric charge, if an electric current will produce a magnetic field, can a magnetic field in turn produce a current? And they both experimented with this and both determined that yes, it can. And actually, the American Henry did his work and made the discovery a little bit earlier than Michael Faraday. But Michael Faraday was the first to publish. And he also did a whole lot more quantitative, empirical work to not just show that it happens, but he quantified it and made measurements and whatnot. Here in figure 21.1 on page 591, there's a picture of his very first setup. He took a battery and an iron ring, and he coiled a wire around that iron ring. So it would produce a magnetic field inside the solenoid. And the iron ring would then, in turn, concentrate that magnetic flux. And he brought the other side over here and hooked it up to a galvanometer. Hook the battery up to the one side, produce the magnetic field. Nothing. He found absolutely no current whatsoever. Then he noticed something. And when he closed the switch, when he first closed the switch, the galvanometer would peg. It would move. It would deflect strongly in one direction, but only for a moment, and then it would drop back to zero. So he saw that when he first closed the switch, he got a pulse of current. More importantly, he found whenever he opened the switch, he got the same pulse of current, but in the other direction. The needle deflected the other way. So when he closed the switch, it opened the switch. And he concluded that it wasn't the magnetic field causing the current directly. It was the changing flux that was inducing the current to flow in the other wire. Changing magnetic field. And if you see this picture on the chapter picture, the heading there on page 590, that big coil, and the bar magnet going in and out of it, this is basically one of the experiments we're going to do, I think next week, on induction. Where you move that magnet down into the thing and you watch the galvanometer deflect, and you pull it out and watch it deflect the other direction. So, he found that a changing magnetic field induces an electric current, or stated differently, a changing magnetic field induces an EMF, an electromotive force. All right, I'm going to try to draw, you know what, I'm not even going to bother trying to draw figure 21.3. I'm just going to draw 21.4 up here. Now, when we describe the orientation of the magnetic field to the closed loop, or to the plane of area, we're talking about this angle. When the magnetic field is perpendicular, that is 0. When it's at an angle, we're talking about the perpendicular to the plane of that the flux is passing through. What will become the face of the coil of wires in a minute, but for now it's just an imaginary plane. And when it's parallel, it's at 90 degrees. That means before we talked about, when we were talking about the force producing the torque, we were looking at the parallel component of the magnetic field to the face of the loop of wire. Now we're talking about the perpendicular component of the magnetic field passing through this area, or through the area of the loop, or whatever we're talking about. Again, for now, we're still an imaginary unit of area. So the magnetic field perpendicular becomes B sub naught times the cosine of the angle. And that's the perpendicular component of the magnetic field. So when it's at 0 degrees, cosine of 0 is 1. You've got the full magnetic field passing through that area. At some angle theta, then it becomes B sub naught times the cosine of that angle, which would be this component here, whereas this would be the parallel component. And then finally, when it's at 90 degrees, cosine of 90 degrees is 0, because here none of the magnetic field is perpendicular to the unit area, or passing through the unit area. And that's what we're looking for here. We're talking about how much of the magnetic flux, how many of the lines of magnetic flux are actually passing through that little unit of area that we're dealing with. Now, here in the book they use the Greek letter, the uppercase phi. As the symbol for the magnetic flux that's passing through the unit area. And it's, well, the magnetic flux is simply equal to B times A. Times the area. Now, that means we're going to introduce a new unit. The Weber, or Weber. Pronounce it however you care, however you please. And it's equal to Tesla square meters. So when we talk about magnetic field, we're talking about B itself, the actual magnetic field, the lines of force, B sub naught. And the units of B sub naught are, somebody? Tesla, thank you. The units of B of the magnetic field are Tesla, or Gauss. Unit of magnetic flux is not. Magnetic flux is measured in Webers or Webers, and it is defined as 1 Tesla per unit area, or per square meter. I'm sorry, not per. Tesla meter squared. Now, what Michael Faraday discovered was that you could calculate, he actually quantified the EMF that was induced into a conductor as minus the change in flux, phi sub b. Per change in time. That if the flux is static, if it's not changing, then the EMF is zero. The induced EMF is zero. But when the flux is changing, it induces an EMF proportional to the rate of change in the magnetic flux, minus the change in magnetic flux per change in time. In calculus, this would be the minus the first time derivative of the flux, the magnetic flux. Now, if that area that the flux is passing through happens to be a conducting wire, this is the amount of EMF that will be induced in that conducting wire, that loop of conducting wire. And if it is a coil with many loops, within loops, then the total induced EMF will be equal to the number of wires, the number of loops, times the change in flux per change in time. So in other words, if this area here, instead of just being an imaginary area, if it was a loop or a coil with a coil of N loops, then the induced EMF would be equal to N times equals minus N times the change in flux per change in time. Thank you. I want you to note that that is all very quantifiable. You can measure the time rate of change of the magnetic flux. You can count the number of loops in a coil of wire. And that means you can calculate an actual voltage, a quantified EMF of X volts that's induced by a changing magnetic field. Let's look at example 21.1 on page 592. A square loop of wire with a side of 5 centimeters in a uniform magnetic field of 0.16 Tesla. What is the magnetic flux in the loop, A, when it's perpendicular to the face of the loop, and B, when it is at an angle of 30 degrees to the magnetic field? All right, well, at 0 degrees, what's the flux through it? Somebody? Times the area of the loop times the cosine of the angle between them. What's the area of the loop? 5 centimeters squared. So that's 0.05 meters squared times the cosine of the angle. What's the cosine of 0? Times 1. Okay, what's 0.05 squared? They did the math, I'm sure. 2.5 times 10 to the minus 3 square meters. Okay, what is B sub naught? You gave us that at what, 0.16 Tesla? So that gives us an induced EMF well, actually, we're looking, at this point, we're just looking for the flux through the field. That gives us a total flux through the field of, somebody do the math. Somebody punch in the numbers into their calculator. 4 times 10 to the minus 4, what? Weavers. Newton meters squared. Okay. That's A. Now they ask, what about when it changes to 30 degrees? When it moves to 30 degrees. This is at 0 degrees. What's the flux at 30 degrees? Still 0.16 Tesla. Still 2.5 times 10 to the minus 3 meters squared. Now it's times cosine of 30 degrees, which is what? Is that a half? I don't remember the unit circled. Square root of 3 over 2. Okay, well, do the math. It becomes 4.0 times 10 to the minus 4 Webers times the cosine of 30 equals Webers. Somebody want to confirm that? .0 times 10 to the minus 4 times cosine 30. I was about to say, I think you might have been in radian mode. You get this time something like 3.5 times 10 to the minus 4. Okay. That's fine. 3.5 times 10 to the minus 4 Webers. So that's the flux through the loop of wire, the one loop of wire, at 0 degrees and at 30 degrees. Now, and for part C, it asks, what is the magnitude of the average current in the loop if it has a resistance of 0.012 ohms and is rotated through that 30 degrees in 0.14 seconds? So we have resistance is what? 0.012 ohms. Is that right? Yeah, and it rotates through 30 degrees in, what, 0.15 seconds? 0.14 seconds. So, how much current is going to be induced? Well, we know that the EMF is going to be the change in the flux per change in time. So the change in flux is going to be 4 times 10 to the minus 4 minus 3.5 times 10 to the minus 4 divided by 0.14 seconds. Somebody do the arithmetic. .6 times 10 to the minus 4 volts. Is that what anyone else got? Okay. Well, if that's our induced voltage, our induced EMF of that many volts, we divide that by 0.012 ohms, gives us what induced current? .8 milliamps for 0.14 seconds. They actually rounded it off to 30 milliamps. Now this brings us squarely to Lenz's law. Lenz's law. How many of you actually noticed that when I did the calculation of the current that flowed, I just completely ignored that minus sign out in front of the Faraday's law. EMF would be negative the change in flux per unit time. This is the whole point of that negative sign. Lenz's law. It says that any current induced by a magnetic field will always produce a separate magnetic field, because anytime you have a charge moving, it produces a magnetic field. What Lenz's law says is that when a magnetic field induces a current to flow, the current will produce a magnetic field that opposes the magnetic field that induced it. That's the whole point of that minus sign in Faraday's law. That it's going to push a current that will produce a magnetic field that will try to maintain, maintain the existing magnetic field. So, if you have a loop of wire, and you have a magnetic field that induces a current to flow this way, what direction does that magnetic field have to be? The magnetic field that the current produces will come this way right? Am I right? Am I getting this right? Is this a right-hand rule of thumb? Because it's not like there's only one. Okay, but what is the direction of the magnetic field that induced that current to flow? You've got a magnetic field. It exerted a force in this direction on the electrons in that wire. What is the direction of force? What's the right-hand rule of thumb for the direction of the force that a magnetic field exerts on a moving charge? Point your fingers in the direction that the charge is moving and turn towards the magnetic field, and it will give you the direction of the force. I don't remember. I think they describe it here. Yeah, that's where they're just telling us what Lenz's law says. Okay, here, look on page 593. We've got these two figures down at the bottom of the page. Is everybody there? Can you see them? In the first set, the upper pair, they take a coil of wire that's in a circle, and then they pull the two edges to collapse the circle. And what they're doing is they're reducing the area of the magnetic flux contained in that coil, in that loop, that coil. Now, when they reduce the area, what are they changing? They're changing the amount of flux passing through that area, which induces an EMF that causes a current to flow. Now, here it shows the magnetic field pointing into the board. And it shows the current flowing clockwise around that loop. Now that says that loop, that current is going to, if you point your thumb in the direction of the current, your fingers coil in the direction of the magnetic field, and that shows that the magnetic field that the current induces is going to be in the same direction as the magnetic field that induced the current. Why? What's happening there? How is the magnetic flux inside the area, how is it changing? When the area gets smaller, the amount of flux through the area is decreasing, getting smaller. So the current induced by that change in flux is going to add to the amount of flux inside the area to try and maintain the amount of flux that was there to begin with. And therefore oppose the induced current flow that comes from reducing the amount of flux in the passing through the area of the loop. See? If you then went the other way and pushed the two ends back together to make the loop bigger, which way would in this case, which way would the current flow? Make the loop bigger, the current's going to flow in the opposite direction because now it's going to be pushing the flux lines out of the page, subtracting from the amount of flux passing through the loop, trying to maintain that lower amount. It's always going to generate a magnetic field in whichever direction will maintain wherever it started. So if that means the flux is getting smaller, if the flux is being reduced, then it's going to try and add to that existing flux. And if the flux is being increased, it's going to try and subtract from that flux. That's Lenz's law. The other way it can happen is if you take that coil and keep it as a circle, but spin it inside that fixed magnetic field. As it rotates, the area perpendicular to the field, the perpendicular component of the flux, changes as a function of angle from maximum, from full B sub naught at 90 degrees, at 0 degrees, to zero flux at 90 degrees. So it's going to go from maximum to minimum, to maximum to minimum, back to maximum in one full revolution. Only what's going to happen on the backside? Let's look at this. We've got our coil of wire and our magnetic field going into the board. As it rotates this way, from 90 degrees, it starts rotating. When it starts to rotate, the flux starts to decrease. Which direction is the current going to flow? It's not going to flow this way because that would subtract from the magnetic flux. The flux is starting to decrease. It wants to maintain, so it's going to point, the current is going to go this direction. Then it gets to 0. Now, as it continues turning, which direction is the current going to flow? Because now it's going to start increasing the flux. So it's going to flow in the opposite direction to try and maximize the flux. To try and minimize the flux, because the flux is now starting to increase the area, and it's going to want to keep the minimum flux. So now the current is flowing in the opposite direction until it gets here, and as it rotates, it starts flowing in that direction again. What that tells you is that as the thing rotates, the current is going to start flowing one direction while the area is decreasing, and in the opposite direction while the area is increasing. You're going to get an AC current flowing. Everyone see that? Oh, we're going to get to that in section 5 with generators, how they can produce the DC with one configuration or AC with a different configuration. And we're also, wasn't actually part of the original plan, but I at least want to touch on chapter 21, section 6, back EMF. Remember we encountered that yesterday in the lab with the where you couldn't make it want to spin the other direction because then it would produce a back EMF that would slow the rotor down until it stopped. But those are coming. Anyway, this is Lenz's laws. Anybody have any questions? All right. Well, then I will see you all Friday. Let's see if we can finish up this through section 7 on Friday. Yeah. No, week 9 was last week. This is week 10.